application. And this will be followed by section 3, where I will kind of apply the theoretical part on a particular example. This will be followed by analyzing further a little bit this particular example and summary and future work, so basically of the problems. So I'm a default student in systems biology in Oxford, and my supervisor is Radek Erwan. I'm mainly interested in stochastic and hybrid models that pop out in systems biology. And this more precisely entails construction of test problems that might be useful for numerical methods or for analysis in general, and then analysis of stochastic effects and numerical artifacts that are often hard to distinguish. In this topic, I will mostly present one. In this presentation, I will mostly present one topic, which is how to construct chemical reaction networks that have properties that we kind of prescribed. And this can be kind of seen as kind of regularizing ODEs from different areas of mathematics so that they can become chemically plausible. And the results presented here are part of the paper that is in the submission process. And this paper was done with Radek and collaborator Tomislav Plesa. I'm also working on another project that might be of interest. I will just briefly mention it. If some of you are interested, please do talk to me, which is more about regularizing PD models in systems biology. So in particular, models of chemotaxis. And once we kind of regularize such models, what kind of effect this regularization has on properties such as blow-up, effective diffusion, and how it affects bed informations. But this is kind of off topic, so this is more mentioned here if you have any interest, so that you can talk to me. So I'll start with motivation, kind of theory. So chemical reaction networks under the mass action kinetics are very often used in systems biology. And mathematically, they take a form of a system of first-order ODEs with polynomial right-hand sides, so quite simple. But these equations can kind of capture so-called chemical exotic phenomena, which mathematically just mean a multi-stability, limit cycle, and chaos. And because they can kind of incorporate such complicated phenomena, this is really the reason why they are so applicable, because they can capture a lot of biological processes. So in most problems in applications, take a form of so-called direct problem, where we are given a reaction network. So we are given a set of chemical reactions as an input, and output is that we have to find some kind of property of the network. So this property can be either number of fixed points, it can be a stability of fixed points, limit cycles, and so on. However, so this is the motivation for a reverse problem. In systems biology, chemical reaction networks are often very high dimensional, and they can have stochastic effects that can have a lot of influence on the dynamics. And this makes the direct problem difficult. So if we are given a reaction network that is very big in systems biology, and we are asked, for example, to determine stochastic bifurcations in the system, this can be very difficult because the system can be very complicated, and it's very hard to distinguish what is coming from the noise, what is coming from the structures in the phase plane. So this is on one hand, and on the other hand, in synthetic biology, instead of having a reaction network and then deriving its properties, we actually want to construct a reaction network that can then be implemented in living organisms. And proof of this concept is the reprocelator. So it's quite famous network that was constructed and then put into the cell and it perform a function. So these two kind of areas, systems biology and synthetic biology, they motivate us to kind of construct chemical reaction networks. And this leads, so in systems biology, this will then lead to so-called caricature models of certain dynamics. They kind of show these exotic phenomena and stochastic effects. In synthetic biology, they will act as blueprints. And in numerical analysis, they can also be very useful because you can construct some kind of pathological reaction networks to check whether your numerical method really works in the real-world problem that can contain kind of this exotic dynamics. And we kind of aim that these caricature models are low-dimensional, and this is what we mean by simple, because dimension is very, very important for analysis in mathematics. And this kind of problem of how to construct a reaction network can be formulated as a constraint inverse problem. So it basically looks like this. We are given a set of properties or constraints that our target network must have, and then we want to construct such a network that has these properties. And given a set of properties, we don't have any guarantee that a network will exist, nor that it is unique. So this is how the algorithm to solve the inverse problem looks like, and I will go then into detail in the last two steps. What is this? Okay. Okay, and we're back.
Well done.
So yeah, it's magic. So the first step is basically that we have certain properties, and we map them to polynomial ODEs. So we map them basically to a polynomial function, to the right-hand side of our ODEs. The second step is then to transform this polynomial ODE to a polynomial ODE that can be actually represented as a chemical reaction network. And this is very important. Not every polynomial ODE can be represented as a reaction network, and this is kind of the crucial bit here. And the final step is, once we have so-called kinetic ODEs, or ODEs that we can represent as a chemical reaction network, then we can kind of derive a chemical reaction network of our desire. So step one will vary greatly depending on what kind of property we want to implement into our ODEs. But step two and step three do not vary that much. So they can be kind of stated once and for all, and they can be then reapplied. So I will then first go into the step two and kind of clear things up, because it's a little bit complicated, and then step three, and then we are done with the theory. So to kind of explain what is the problem in step two, so when we want to transform polynomial ODE to a kinetic one, we kind of introduce this kind of notion of cross-negative terms. So if you look at this kind of very simple two-dimensional system of ODEs that model chemicals, this is actually from Alan Turing's famous paper. You can see that this term that is in the rectangle. So if you think about it, this term cannot be represented as a chemical reaction network. And to kind of see this, if you set this right-hand side, if you evaluate it at x1 is equal to 0, so if we assume that our chemical species x1 is the concentration is 0, the right-hand side will look like this. It will have minus 6x2 plus 1, so it can become negative. So what this implies is that when the chemical species x1 is absent, so there is no concentration available, this process still consumes it, and this is chemically impossible. So if you don't have a chemical reactions cannot consume it. So if we want to kind of write a chemical reaction network for this system, we cannot do this. So this is not possible in this form. And this then leads us to kind of define in a kind of orderly way the right-hand sides of our ODEs that pop out in mass action kinetics. So we have a space of polynomial functions of order m, and we can kind of write them as a union of all the polynomial functions that do not contain these cross-negative terms. So we denote them by k. So and the space is denoted by bmk. So this is the space of polynomial functions that are kinetic. They are nice. We can kind of map them into reaction networks. And then we have non-kinetic functions n in the space Bmn that do contain cross-negative terms. Okay, so
Can I ask a
yeah,
question?
yeah.
Oh, who's that?
Go ahead, Rachel.
You want to start? Or you want me to start?
Go ahead.
Well, actually, I have a question from your step one to step two.
Mm-hmm.
Because if you're saying you want a set of properties,
Yeah.
then are you saying that those properties don't include the fact that, for example, in your example, the case where x1 can be consumed when it's...
Yeah,
And so, I mean, does that mean you're leaving out some physical properties?
yeah, you could, if you want to, you can define that this kind of kinetic terms, that you can require that in step one. But the reason why I did not define it in that way, as you are suggesting, is because we can develop systematic methods to eliminate these terms, but we cannot develop systematic methods to build in other properties into our network. So it makes more sense to say, okay, we will define these kind of properties that may or may not be possible to map, and then whatever we get, we can always make it kinetic. Does that make sense?
I guess the proof is in the pudding, but yeah, go ahead. Peter, yeah.
All right. Can you go to the next slide? There are two things confused me.
Sorry?
Next slide, there are 2 points of confusion. So
Okay.
the next one after this.
Okay.
Okay, so first of all, if you had a term that was like minus x1, x2,
Yes.
which does vanish when x1 is 0, do you call that cross negative
No.
or not? Okay, and so what you, then this last thing where you say, so cross negative simply means you have a term that can be negative even when the
Species is
species
zero.
is zero, okay.
Correct.
And so when you're seeing the last point, they are non-negative, so how can you have how can you have a non-kinetic thing that's non-negative?
Well, I will show you by example.
Okay.
So this is kind of slightly unintuitive, I guess.
But you said, you defined non-kinetic to mean that they contain a cross-negative term.
Yes.
So how can you possibly drive a species to negative value?
Well, the point is that not all the system can have cross-negative terms and still be non-negative. I have an example,
Okay.
so it will be clear. So yeah, so this is important. So this is what is a bit slightly confusing. So non-kinetic functions, so functions that do contain cross-negative terms, they can be non-negative. So if I give you a phase plane of, let's say, two chemical species, and everything is contained in the first quadrant, nothing goes out, you cannot immediately say this can be represented as a chemical reaction network. You have to look at the structure of the equations.
Okay, I guess maybe my question is the pronoun they. So what is if they are non-negative? Is it the
So
terms?
it means kinetic functions. So so those which means polynomial functions that do not have cross-negative terms. So they are always non-negative. So kinetic functions, so functions that do not have cross-negative terms, are always non-negative. Does that make sense?
All right. Keep going.
I think maybe examples will kind of be
Okay.
better explained. Any other question? Okay, so this is the very important kind of statement that I just kind of want to emphasize is that only kinetic functions can be represented as a chemical reaction network. So what you have asked is basically why I emphasize this. It's not enough to require that they're non-negative. They have to be kinetic. So here's an example. So we have two equations. And we can immediately see that the second equation is kinetic. It only contains a positive term, so everything is fine. But whether this equation is kinetic or non-kinetic will depend on our parameter k. And so if we set x1 is equal to 0 here, so and check out how our function looks like. It looks like this. And we know immediately if k is greater than 0, our function is kinetic, everything is fine. But if k is less than 0, then our function is not kinetic. However, if k is between -1 and 0, this does not this does not have any you know what I mean? So this doesn't have any real roots. So this function is non-negative nonetheless. So if someone gives you a phase plane and it looks like the function is non-negative, this doesn't guarantee that you can represent it as a chemical reaction network. Does that make sense? Okay. Okay. So this is kind of where the second step is kind of leading towards. So what we have basically said is that the set of all polynomial functions, we can kind of write it as a union of kinetic and non-kinetic. And the important bit here is that if we are given a random polynomial function, it is much more likely that it will be non-kinetic, which means that in the first step, after we are done with the first step, we are much more likely to end up with a non-kinetic function.
So what probability measure on the space of systems are you using when you make that statement?
I do not know. So, but I can definitely refer you to a paper that has explored this in greater detail. So
even intuitively, I mean, so what do you mean by choosing a random?
So it means that, let's say that you fix m, so order of polynomial functions, let's say to 10, and you randomly keep generating polynomial functions. The likelihood that you will, so on a computer you generate coefficients in your polynomial functions.
Uniformly over some range or what?
Yeah, uniformly over some range. Then it will be the case that kinetic functions will be rare because they have to, everything has to be positive. So to kind of overcome that, we kind of introduce these kinetic transformations that will always map non-kinetic into kinetic functions. So the way we define them, and this is the last kind of more elaborate definition, the way we define them is given a polynomial function, so it can be kinetic or non-kinetic. Obviously, it's going to apply if it's non-kinetic. We define a kinetic transformation psi that if it has two properties. Firstly, it will map this polynomial function to a kinetic function. So this is what we wanted to do. And the second is that these two functions, so the input non-kinetic function and the output kinetic function, they have to be locally topological equivalent near their common fixed points, which means that once we transform a non-kinetic function into a kinetic function, we want their phase spaces to look similar, because we can distort the dynamics too much. So we want to preserve the dynamics. So for example, we do not want to destroy limit cycles or change the stability of fixed points, because that will change the nature of our model that was derived. Okay.
Wait, can you go back? Sorry, I'm still trying to.
Yeah.
Is there an implicit assumption here that the fixed points are non-zero or not? Because it
Uh,
seems like
so-
you're changing the dynamics near zero.
Very good point. Yeah. So this holds for fixed points that are mapped into the non-negative ortant. So that are mapped where the chemistry is. So for these fixed points, they have to be of the same type as the previous fixed points in the function, wherever they were. Other fixed points in the input function that are elsewhere, that are not mapped into the first quadrant, we don't care about them. They can be changed. We don't care. So as long
But
as...
what about the ones on the boundary? That's what I'm saying, because you're changing your dynamics
Yeah,
near the boundary.
that will
right?
depend on particular transformations we apply, but generally, kind of, we want to push them outside of the boundary, the fixed points. I mean, it can be overcome, but yeah. Okay, and so just kind of something to notice is that when we map our polynomial function into the kinetic function, the reaction rates will change, and the dimension of the system can change, as can nonlinearity. So, so ideally, one would want to find kinetic transformation which is affine, and the reason is that in that case, the dimension of the system doesn't change, so we have the same number of chemical species, and the nonlinearity doesn't change. So if the system was order 2, it is still order 2. This is what we would like ideally. However, this is often not possible, and we need to apply kind of nonlinear transformations in composition. So, so how these nonlinear transformations work, they basically replace cross-negative terms by so-called extractorable terms. So if we have a term in, well, I will show by an example. And so I will discuss two such transformations. The extractorable transformation that was derived in the 80s, and I just kind of, in the paper, explore further its properties, and the quasi-steady-state assumption transformation, which we kind of derive in the paper. There are two more, but they're kind of inferior. So, by an example to show how extractorable transformation looks like. So, we start with our system that we have, so Turing system, and we have this cross-negative term. And so, what we basically do is we multiply this equation by x1 and this equation by x2, and we get this system. And now you can see that this term is no longer cross-negative because it's multiplied by x1. Of course, we do not have to really multiply this by x2. We can only multiply the first one by x1 and just don't do anything with the second equation. And so what we obtain basically is a kinetic system. So it can be represented as a chemical reaction network. But what we have introduced is additional fixed points on the boundary of this system. And also, we could have destroyed topological equivalence near common fixed points. And in 1D, which is quite low, but it's still applicable, we have derived in the paper conditions that ensure that these two systems are topologically equivalent. So you can ensure that. So this is how extractorable transformation kind of works. So basically, at an expense of multiplying this by x1, we kind of have to multiply every single term by x1. So we kind of stay at the same dimension. So this is still two-dimensional. However, we introduce two more nonlinear terms. So instead of having order 1 and order 0, this is order 2 and order 1. The second transformation is the quasi-steady assumption transformation. And again, we apply to the same example. So what we here do basically is we multiply this again by x2, but this time we do not multiply the rest of the terms by x1, sorry, but we instead multiply it by a new species, y1, that then satisfies this equation. And as you can kind of see, as mu goes to 0, intuitively, y1 will be 1 over x1, and this will cancel. This is just kind of intuitive, but this can be proved that as mu goes to 0, these two systems are dynamically equivalent. So they have the same dynamics. So in this case, we have introduced less nonlinearity, only one nonlinear term, but we have also introduced one more dimension. So we have increased kind of the dimension of the system. So these are the two transformations, and this kind of finishes the second step, which was kind of the most elaborate. So now that we have kinetic functions or kinetic system of ODEs, we kind of want to write down a chemical reaction network that corresponds to this system. And the thing is that for each kinetic ODE system, one can write many reaction networks. And these are usually done by computer, so you kind of code it, and you can have reaction networks with certain properties. Here we kind of will derive so-called canonical reaction networks, which are special because they can be done by hand. So you can always, for every single system of kinetic ODEs, you can always by hand write a chemical reaction network, and this is very nice. So again, I will show by
Sorry,
example.
can you go back to the previous slide?
Here?
Yeah, let me just, so is there a reason why you didn't just multiply by y1 and take mu dy1 dt equals 1 minus y1? Does that, how does that not work?
So if you multiply only by y1 and then
And then just drive y1, have it relax to 1. Is that not kinetic?
well, I mean, you will have the non-kinetic term here. You'll have, so
dy1 dt equals 1 minus y1 is not, it has
oh, okay, I see what you're saying. Okay, let me just think. So I know that there is a reason why this doesn't work. So if this is,
Well, dx1 is still not negative. You need the negative.
yeah,
x1.
of course, yeah. So yeah, basically the question
okay,
is that
right.
it has to be multiplied by x1, otherwise this stays.
You're basically undoing that.
I see. Okay.
So excuse me, what was the statement here that this system is positive with whatever mu you put?
Positive?
Whatever coefficient mu you choose?
Oh yeah. So these two are equivalent in the positive orient. This means just kind of first quadrant. Does that answer it?
For all mu or just
No, as mu goes to 0,
is small.
in the limit.
In the limit.
So they are asymptotically equivalent. So they are not equivalent. So for each finite mu, you don't have a guarantee that they're
Okay.
equivalent.
So in practice you can.
In practice, you take 0.01 and then it works.
Okay.
So yeah, so just the intuition then is, so you want to multiply by x1 to make it not cross-kinetic or whatever.
Yeah.
And then, but that's not good because that changes the properties of the equation. So then the
Correct.
y1's to recover, which what Dave was
Yes.
suggesting is
Okay, so now I'll just kind of demonstrate how to construct this canonical reaction network. So let's say that we are given this system of ODEs, so quite simple. So the way we kind of construct this canonical reaction network is for each term in each equation, we will have one chemical reaction. So in this system, we have two terms, so we will have two reactions. So how we do it is basically we take the first term here, and our reaction network will have coefficient K1 as a rate constant. It has to have on the right-hand side x1 plus x2, or s1 plus s2. And since it has a minus sign, we demand that only one species changes, and in the first equation it has to be x1. So s1 has to decrease by 1. And this is the first reaction. If you look at the second term, again it has K1 as a reaction rate. On the right-hand side, again it has S1 plus S2, but here we have a plus sign, which means that X2 has increased by 1. So we have S1 plus to S2. And this is the chemical reaction network that corresponds to this system for these. Note that another induced network is this, which is clearly simpler, but you have to think about a little bit to derive it. And if you have a more complicated system, you can't really, without a computer, derive simple reaction networks. So this is just to illustrate that canonical reaction networks are not the simplest by any means. They're just doable by hand. So you can just kind of do it.
So sorry, because I missed the definition of the canonical one. So a canonical reaction network is a network that for whichever polynomial term has a reaction.
Correct.
Okay.
Yeah. And to be more precise, so each term will induce a reaction, and in each reaction, only one chemical species will change, and it will change by 1. This is the definition. So okay. So this is basically it. So now we have kind of like overviewed the framework for constructing network, and now I will kind of apply it. So this is kind of nicer. So so we choose to kind of apply it to construct two-dimensional systems because they are very easily analyzed, and they can still exhibit exotic dynamics, limit cycles, and multistability. They cannot have chaos, but they can still have this kind of two interesting exotic dynamics. And we also choose to kind of incorporate into our system a supercritical homoclinic bifurcation, because this leads to our system having both limit cycle and a stable fixed and bistability. So it's kind of interesting dynamically. So just to kind of briefly remind what homoclinic bifurcation is. So here at alpha is equal to 0, alpha is our bifurcation parameter. we have at the origin a saddle, and we consider the unstable manifold of the saddle kind of loops around and goes back into the stable manifold, and so we have a homoclinic loop, a loop that connects a fixed point to itself, and this forms a limit cycle. And then if we move away from the bifurcation, in this case the limit cycle kind of moves here, and it is no longer homoclinic orbit, and in this case the limit cycle is destroyed. So basically we have a homoclinic loop that can break in and destroy completely the limit cycle, or that can kind of transform itself into a limit cycle that is not a homoclinic loop. So this is how it kind of looks like. So we couldn't really find in two-dimensional kinetic ODEs that would display such a dynamics. So that was the additional motivation to kind of construct this. But this does occur in biology. So for example, there are a few papers that study this kind of how frogs' eggs develop. And this system contains 9 chemical species and 9 chemical reactions. And it has many structures in the phase space. And one of them is this homoclinic loop. So it does occur in biology. It's not completely artificial. But in this case, there are so many structures in the phase space that we cannot really say what the effect homoclinic orbit has, because it's surrounded by other fixed points and limit cycles. And so by constructing a nice, simple canonical example, we can really see what the effect is. So we go on the first step. So the first step is to map a property to a system of ODEs. So this was partially done, mostly done by a previous paper. They chose this loop, which is called L'Hopital's cubic. It kind of looks like a homoclinic orbit, as you can see. It kind of, yeah, it looks like a homoclinic orbit. And so one can kind of take this formula, which is this L'Hopital's cubic, and take a polynomial system of functions that with undetermined coefficients, and require this condition, so that basically the system is the homoclinic loop is contained into the system. And this was already done, and the only thing that we had to do in the paper is we had to kind of completely satisfy Andronov-Leontovich theorem, which just basically ensures that our bifurcation happens in a nice way, so in a generic way. These details are not totally important. So what we end up with is this system of ODEs, and there are 2 parameters, A and alpha. And so maybe I should kind of show what happens. So we go from here to here. So we kind of breathe life into it. So here, an example of solution to this phase plane is shown here, and we have the homoclinic orbit, and we have here unstable spiral. Here we have a saddle, and here we have a stable node, and this clearly, has a homoclinic loop inside it. And we have 2 parameters, which is alpha, which kind of regulates our bifurcation, and A, which controls the separation between these 2 stable states. So we can control how far away limit cycle is from the node. So now the second step is basically, the problem with this system is that the loop, which is what interests us, is located in the outside of the first quadrant. So we have to map it into the first quadrant. And so what we can do is we can apply translation, so simple translation. So we can translate our system, and what we obtain is shown here. And what you can see is that although here the homoclinic loop is in the first quadrant, in the red line segments, you can see that the flow goes outside of the first quadrant, so it's no good. So this cannot be represented as a chemical reaction network. And in fact, one can prove that if you only apply translations, you cannot make the system kinetic. So no translation can fix this. So then what we do basically is we apply, after applying translation, we apply, for example, explorable transformation. So the one that was mentioned before. So we just multiply our system by x1 and x2. And we have to ensure certain conditions to hold so that everything is nice, so that systems are kind of equivalent and everything. And what we obtain is this picture on the right. So you can see that it differs from the picture on the left because there is a boundary fixed point introduced. So this is a saddle, and crucially, the stable manifold of the saddle. In this case, it crosses the x2 axis, but in this case, it kind of goes asymptotically towards it. So, and this clearly can represent as a chemical reaction network. So, basically, we end up with the system. So we can also kind of vary the orientations. This can be more relevant for stochastic analysis. So in this case, the node, one stable set, is above the limit cycle, the other stable set, and we can kind of reverse it. so that the node is below. And this can be kind of then studied how the stochastic switching happens. And we can also apply the quasi-steady state assumption transformation, and it leads to this system. It's 4-dimensional because there are at least 2 cross-negative terms. And so, in kind of summary, we end up with this system of 2 ODEs, and each of these parameters depends on our translation, on A and on alpha. And if we write the canonical reaction network, it looks like this. So basically, what we have is we have a chemical system in 2D, which has these exotic dynamics that we can kind of explore.
So is the point of all this that you're trying to kind of do a normal form for some kind of structure that respects this kinetic condition?
In a way, it kind of chemical normal form. I think you can kind of view it like that. I mean, it should probably be more rigorously defined, but along those lines, yeah. Okay, and now just brief stochastic analysis. So, as was mentioned here many times, intrinsic stochastic effects are very important for system biology, and they occur because there are a low number of chemical species. The copy number is low often, and this can have very significant and unintuitive effect on the dynamics. And here we will study what we have, the model that we have derived, by looking at just simulating it with Gillespie algorithm and see how it compares to the deterministic model near the bifurcation.
I have a quick question on the previous slide. Sorry for interrupting.
Yeah.
Is actually the one before.
Okay.
Is it keeping all the chemical species finite depending on the initial condition or system?
In this case,
look on the phase space at some trajectory we are
going away. In this case, we require that the dimensions that are introduced here, they have to decay towards the fixed point, so that nothing goes away to the infinity. So it's controlled. So I think if we go way back, okay, here, I didn't mention it, but it says local dynamics along any additional dimension must asymptotically tend to the corresponding fixed point. So it kind of flows where it should. Thank you. That's a good question. So now we just present very elementary stochastic analysis. So here we choose the separation between the node and the limit cycle to be small. And what we see in red is just solution of ODEs, numerical, and in blue we see a representative sample pad of the Gillespie algorithm. And what we see before the bifurcation, in red, we see that wherever we start our system, we always tend to the node. The node is globally stable because the limit cycle doesn't exist. And in this case, if we start near the node, it will go to the node, and if we start near the limit cycle, it will also be near the limit cycle. And the stochastic model, on the other hand, it kind of switches between the two stable sets before and after the bifurcation, so it doesn't really respect it. But this is nothing too new. What is more interesting is that if we make the stable sets to be larger in separation, so if we kind of separate the node quite away from the limit cycle, the deterministic model doesn't really care, so it behaves in the same way. But the stochastic model tends to the node with very high probability and visits the limit cycle as a rare event, so very infrequently. And this doesn't really depend on the initial condition. So in a way, the stochastic model for large separation behaves like the deterministic model before the bifurcation. So it kind of always goes to the node. The limit cycle kind of becomes quasi-stable, and this is kind of an example of the thing called Kaiser's paradox, where the long-term dynamics of our ODE system doesn't match with the system of stochastic simulation. And this, for example, wasn't intuitive to me, and I think to us, when we derived the model, and we wouldn't predict that homoclinic bifurcation would necessarily lead to something like this. So that's basically it. So to summarize, in the presentation, construction of reaction network was formalized as an inverse problem. And we have defined two transformations that can always map polynomial ODEs to kinetic ones, to the ones that can be represented as a reaction network. And then we have applied this framework to construct 2 and 3-dimensional systems that have homoclinic bifurcation. Some open questions and future work regarding this project is first to kind of study in more detail how our stochastic behavior of the system depends on the volume and the parameters a and alpha. That's the first thing. The second thing is, so we have constructed now two-dimensional system with a homoclinic orbit, with homoclinic bifurcation. But what would be interesting is to construct a series of two-dimensional systems that have complicated dynamics, so multiple limit cycle, and see what kind of thing noise does there. So in quadratic 2D ODEs, these are all the possible configurations of the limit cycle. So we can have 1, 2, 3, 4, and each of the systems exists already that has these dynamics, but they are not kinetic. So they're polynomial, but they're not kinetic, and one can then check whether they can be easily transformed into kinetic, and then once they're transformed, to actually study them in detail. So what kind of effects noise will play here, for example. And the final thing that can be done is so-called second part of Hilbert-16 problem, where it has actually fairly recently been shown that in 2D, quadratic polynomial systems can have maximally 4 limit cycles, and they're in configuration 3.1, so it's here. So this is the most that quadratic systems can have in 2D. And one can also ask the same question for kinetic ODs. Is this true for them? So in other words, one can ask the question, if we have two chemical species that interact quadratically, which is what is considered to be chemically plausible, what is the maximum number of limit cycles that one can have? Is it 4 or is it less? So yeah, so that's basically it. And if you want to discuss about anything about the project that I've just mentioned, then please do talk to me. So yeah, thank you for the attention.
So going towards what Pete said, so a long time ago you had the 3 steps to this algorithm, right?
Yeah.
Step 1 was you have a property and you map it to a polynomial system. Step 2 is mapping from a polynomial system to a kinetic system, and I forget step 3.
Step 3 is mapping kinetic ODs to networks.
Sure. Okay. So where's the? So it seemed like step 1 is the key part. Or, I know you focus on step 2 theoretically, but step 1 is like if I have some property, the hard. I mean, is that the hard? That's what I'm asking.
Yeah.
What's the hard part? Is it?
Well, I mean, before I've collected and kind of formulated the second step, it was spread across the literature, and methods didn't really like exist as such. But step 2 can be done kind of systematically.
Wait, step 2 is hard.
So mapping any ODE to kinetic ODE. So having nice ODEs.
Getting rid of the cross-negative term and all that.
Yeah.
But I thought that was done already, right? The multiplying by x1, x2.
Yeah, that's the second step. So let me just go back. So the first step, so I assume that most of the systems that will be constructed will be done by only doing step 2 and step 3. Because in the literature, in physics and whatever you want, there are already equations that are polynomial, and if they're not polynomial, we can map them to polynomial ODEs that already have any kind of dynamics you want. And so we just have to follow step 2 and step 3. Step 1 is certainly the most creative,
for sure.
But it will also be mostly useless, because in most cases we will already have from application some system that we will just want to move to chemistry. So and yeah, so they're kind of sufficient.
In particular, step 1 is not systematic.
Yeah, it's totally not
It's
systematic.
like
It's like yeah.
I want something that does.
I mean, one could formulate, I guess, one could, for example, ask if we have algebraic curves, what kind of properties do they have to have so that they are mapped to a system of polynomial ODEs? And then one can see that this homoclinic loop was an example and see what kind of loops can be mapped. That could be like systematized, I guess. But other than that, yeah.
So but for step 2, when would it not work just to multiply like dx1 by x1?
Oh, for example, there are systems that if you multiply it, let me just kind of, is there a board here?
Oh, I see what you're going to say. You get a chemical system, but it's not one that's going to give you the same properties.
Yes, or even more fundamentally is, for example, if you have a system like let's say like this, 2 limit cycles. So you have 2 limit cycles, and you want to map them in the first quadrant. So these 2 will be in the first quadrant, but you need to have some kind of fixed point on the boundary, right? Because otherwise the flow will go around the limit cycles and it will go outside of the first quadrant. And in this case, it might be that you will introduce in the origin a saddle that will push the dynamics to infinity below again. So in other words, there is problem with bounded solutions. So these kind of transformations can also lead to the system going to infinity. And if only I could show. Okay, so for example, to construct this, it wasn't as simple at all. So if you look at what steps were used here, we just used translation and extraorbital transformation. But if you look at what had to be done here, we had to apply 2 more transformations to actually have it reverse without a species going to infinity and with having everything equivalent. So it isn't always straightforward.
So I guess, sorry, I'm slowly getting to my real, so is it algorithmic what you have at the end of the day, or is it still an art to some sense? Like, I want certain property X, and I don't want explosions on this boundary, and I don't want this, and then you sort of have to massage it.
It's still slightly like art. It will depend on the system.
In the property, presumably.
Yeah, and limit cycles without any isolated fixed points will be slightly a problem because you have to kind of fine tune everything. But yeah, so interesting question is whether this can be completely systematized so that computer can do it and so on. There are transformations that can do this kind of more systematically, but they tend to introduce much more nonlinearity into the system. So, for example, there is this kind of reparameterization of time, where you multiply your time by all the species in the system. And so you get a system, and people do this. So there are papers that they study the systems, and you get systems of order like 5. And sure, you can do it systematically, but this is not biologically plausible, and it's very nonlinear, so it's not very nice numerically. So yeah, I guess it's not that simple that it can be, at least to my mind, at this point, totally algorithmic.
Yeah, so, you know, the end where you're showing the stochastic simulations, it points to kind of another issue, I mean, which you've already kind of said here, right? Which is, so you have your, whatever system you started with, you transformed it, and it matters a lot whether these various structures that you have sitting there in the deterministic or mean field model are in some sense closed, or you're able to jump back and forth, because as you show in this one, you don't sit by any of them, you do some sort of transient behavior where kind of jumping back and forth and whatever. So it seems that there's another, some other criteria if you're really worried about the stochastic system, which is, do you maintain some sort of the same type of separation of these structures that you would see in, I mean, you would want to maintain that in both systems. So do you have any sense, so, I mean, because otherwise you could just, you know, move everything around and put everything close, and then your noise could totally change the dynamics. It'd be completely different from the original system.
Yeah, so in a way you're kind of asking slightly applied question. So for example, in applications, if we have homoclinic bifurcation, are the 2 structures typically close or typically far away?
Well, I'm just saying your original model, they could be close or they could be far away, depends on the model. And so do you have any sense of how to preserve that sort of structure?
Well, it can be preserved. I mean, I have, in this particular model, for example, I have a parameter that controls how far they are, and I can vary it as I wish. But I think that what the distance between stable sets will be, ultimately, if you're in applied field, it will depend on your application area. And if you're analyzing systems as I do, then you just want to vary everything and see, you know, how things work. So
okay, yeah. So I missed that in here that you actually have a parameter.
Oh yeah,
maybe.
Distance. Yeah, maybe I should have emphasized better. So we have 2 parameters. So this is the model that we created. It's shown here in on the right. So A is this parameter. So A controls the separation between this saddle and this node. And the greater the A is, we kind of slide this node along this manifold. So it's controlled. But that's what's very nice about this model, because there's a single parameter that actually slides this fixed one, which if we were to find in application a model, it's very unlikely that we would have this single parameter that nicely controls it. So it's kind of nice for analysis.
I wanted to mention or note that you somehow seem to assume that the bifurcation happens at alpha equals 1 or something, but is it the same point when it happens in the stochastic system? Isn't it that for stochastic you would need to take the parameter factor? And the reason why you see the same stochastic behavior in both panels is that you didn't take the parameter.
Well, this is kind of very common for stochastic models, that they they don't have a sharp point of bifurcation. So they will typically have, they will typically start to behave according to the bifurcation slightly before the bifurcation. So for this purpose it was fine, but you mean why I didn't look?
In the next, I think I mean the next slide, that you seem to observe one kind of behavior, and isn't it the case that you would observe both kinds of behavior, so frequent switching?
Well, no. But this is the interesting bit about this, is that no matter whatever neighborhood of the bifurcation parameter you take, the stochastic model will behave like this. It's simply because the limit cycle is quasi-stable. So so if you're maybe I should try. So if you are near the limit cycle here in the stochastic model, and noise pushes you slightly like here, you immediately go up. And if you look at how the field looks like, it's very unlikely that you will go counter the field and stay here for a long time. So does that answer it? It's kind of, this kind of picture doesn't depend on which bifurcation point I took, whether I took alpha is 0.1 or more or less. It will kind of look the same. Answer it. Maybe.
So I mean, can you go back to the previous picture?
Yeah.
You were showing with the I'm not
The face plane.
the face plane.
Oh, sorry.
So it's not clear to me, but I mean,
Yeah.
it's not clear to me. I mean, this is a snap for a specific value of A. Yeah.
Yes, correct. Yeah.
So is basically what you're saying is that if you use a different value of A, the green line is gonna go further up.
The green dot,
The
yeah,
green
it's
dot
going
is
to
gonna-
go further up, that's correct. If A is increased, yeah.
Which then means that it's quite far away from the limit circle.
Yeah, yeah, and you can, for example, this is part of the open problem, I guess, is, for example, you can determine at what distance, what should be the distance between these two fixed points so that you obtain this kind of dynamics and explain why stochastically.
Okay.
So there is a critical distance probably between the two stable sets where this kind of behavior kicks in.
And you haven't studied that numerically, or
No. So I didn't go into details with this, no.
Can you go back to the face plane again?
Yeah.
It's a nice base plane.
Is one of these the original system or not?
So the original system is this.
So the first one's just translated.
Yeah, so
So it's just, I see that.
so we have translated it into the first quadrant and then kind of applied this expectorable transformation to fix the manifold of the setup to kind of behave nicely, not to cross the axis.
Did you ever show us the resulting chemical system?
Yeah, I believe so. It is here. So of course these pretty parameters k1 and whatever, they look very nasty. They are full of, they depend on A, alpha, and the translations. And there are also constraints on how much you can translate, because if you translate too much in one direction or the other, the system will not be without cross-negative terms. So the parameters have to be finely tuned, but this comes from the analysis.
And how does the stochastic, how does it look stochastically in the original model?
You simply cannot do it because in this is the original model. You cannot write chemical reactions for this. That's the kind of the whole point. So because this I'm actually, this is not true. So for this model, this model turns out to be kinetic actually. So everything is fine here, but this kind of homoclinic loop that we are interested in is not in the positive quadrant. So if you simulate this system, everything will just go to the node. Because your chemistry lives here, and whatever you start, and this is called chemically regular behavior, so it's boring. We just have the node. So we are not really interested in this. So that's why you kind of map it and then do this kind of magic.
Sort of funny that your canonical model gave 9 equations. Is that what you saw in the frog? Because I would have expected the canonical model kind of makes too many reactions because it tries to be, kind of cautious, right?
Yeah. I mean, it's kind of like
Yeah,
it
right.
can be. It's very hard to predict, but yeah, it's not like too bad. And I'm sure that this can be reduced. So there are algorithms people generate thousands 10,000s of chemical reactions for a given system bodies, and they can specify how much reactions, they can find minimal number of reactions and so on. So if this would be, for example, of interest in applications, one can actually construct much more plausible reaction networks. So this is basically the key part, to have this OD system.
Yeah, I guess my point was, you said before that there was a 9-equation model for some frog egg
Yeah.
that had the bifurcation structure, or bifurcation
Yeah.
structure. And going back to your, probability space of networks thing, right? I would have, I would have guessed that if you pulled something from the literature, say, oh, I want to construct a network that has this property through this procedure, that you would get a larger dimensional system than what you saw in the scientific paper, right?
Yeah, I guess the thing is that this is constructed very efficiently, so there is minimal elements here, while the biological model has a lot of irrelevant structures in the base plane. I mean irrelevant. I mean irrelevant for analysis.
No, because he was saying that it has lots of other dynamical things.
Yeah, it has other limit
And
cycles.
so he just said, no, I don't want that stuff going on. So in
Yeah,
fact,
that's
you've chosen,
So they're both
you've chosen a particular behavior which
Yeah.
eliminates a whole bunch of stuff that you would get in the
Yeah, precisely.
model.
Can I ask one thing? So one more thing. So you also said though that it's plausible to extend the phase space and still kind of have the same behavior.
What do you mean extend the phase space?
So if you go to the previous, the QSSA basically that you wrote afterwards. You wrote the system.
You mean this?
This one.
Yeah.
So that now would sort of be a chemical system with four
Chemical species, yeah.
with four chemical species.
Yeah.
So would you expect to sort of like get similar behavior? I mean, again, there's not really phase play there because you
There's
only have-
phase space. Yeah.
there's phase space, but would you expect to sort of see similar kind of lock-in behavior on that?
Yeah, so this is guaranteed by the theorem that we kind of proved, is that this will have dynamically equivalent, it will be dynamically equivalent to the other model, in the sense that the homoclinic loop will stay two-dimensional, so it will be on the two-dimensional manifold in four-dimensional space. It doesn't kind of grow in dimension. So basically dynamics along these new dimensions is kind of trivial. It kind of just
So and in terms of reactions, how many reactions are involved in this?
well.
I'm wondering, can you sort of like reduce the number of reactions by increasing the number of dimensions? I mean, I guess here you have one.
You could kind of combine it that way, but I didn't really bother because dimensions of reaction, the number of reactions can be reduced by this algorithm that is outside this on the computer. But basically, this will have the same. It will have 4 additional reactions. So it will have, like, if this was 9, this will have 13 because it has the same number of reactions as our system plus 1, 2, 3, 4. In terms of canonical system, right? So it will have 4 additional coming from these 2 equations. And of course, one can also apply a composition of these 2. Yeah.
So with regard to your Hilbert 16th problem, is the idea that you're going to use these transformation? I don't know whether those examples for the original theorem, if those are constructive, so you can try to map them, or
Yeah. So there are 2 approaches that can be done. There are a few systems that look like this, and one can just simply try to map them, and if they map, it's kind of proved by an example. Another thing is that there are sets of sufficient conditions that ensure that up to the quadratic system has this kind of limit cycles. And I have checked 2 out of, I think, 4, and they're false for a chemical system. So unfortunately, it's not like, oh yes, it's straightforward. So the thing that can be done is one can then check other conditions, or just brute force kind of try to map and say, yeah, I have it.
Can you go to the stochastic pictures?
Yeah.
So let me just make an observation that,
Yeah.
I don't know if you guys have looked at this. So the stochastic analog is not well defined for the, okay, so if you wrote, I don't know how to word this. So as you already said, you can write down multiple ODE models for the same polynomial system.
Yes.
Sorry, you can write down, sorry, I said it wrong. You can write down multiple chemical systems for the same, that will induce the same system of
Yes.
polynomial
Yes.
equations.
Yeah.
Each of those chemical systems gives you a stochastic model.
Yes.
But those stochastic models are different.
Mhm.
And they can have quite different behaviors.
That's interesting. Yeah.
So I don't know if you've looked into, because like the picture you're drawing there,
Mhm.
I'm guessing came from.
The one that I presented.
Yeah, like you look at that stochastic system, I'm guessing you took the same parameters themselves, used those as the intensity function, yeah.
So this is basically corresponding to canonical.
And in a sense, so that one's, anyway, okay, maybe this is an offline comment, but it's more, I don't know.
You're saying that whether you do a canonical or non-canonical choice is gonna affect.
It affects the stochastic model, but it does not affect the ODE model, which is an interesting thing.
But I mean, so deterministically, all of these chemical reaction systems should be equivalent.
Exactly the same.
So, and you think that maybe different formulations of the reaction systems can be stochastically slightly different?
Or even more.
No, they are
More
slightly, they're
than
different.
slightly.
They're,
Because for example, if you look at this one, it's pretty clear you have some direction that's fast, right? And you have some other direction that's slower as you're moving back and forth,
Or
right?
just-
Because you go,
but I'm saying something much more basic than that. I'm just saying like, if you have, like go back for a second. If
yeah, but no, I'm agreeing with you
Oh,
by
okay.
saying that, yeah, it could be that if you use a different system, you won't necessarily have that fast, slow sort of thing that you
Sure.
can see in the other one, right?
But I would assume that since the mean field prediction is kind of the same for all these models, that they would behave similarly to each other.
Well, what about your
There's a
first
theorem sitting
example?
there.
What about your most basic example where you had two different realizations of the polynomial? Are those gonna be stochastically close to each other?
Which one do you mean?
The very first,
Very first example?
it was just, minus, x1, x2, and minus x1, x2,
Oh, okay. Yes.
right? So I mean, are equations 5 and 6
Yeah, yeah.
stochastically similar? I don't know.
Yeah, that's true.
Yeah, that's exactly what I was getting at. Exactly.
Yeah, so I guess where these kind of systems can vary is, for example, the efficiency, they can vary in the network, and so reversibility can also be one thing that can be different in the networks. So
Well, no, it's more than that though. Like for example, system 5, you can observe the loss of an S1, right? You could run out of all your S1. The first reaction could just go to zero, like go crazy, and S1 goes to 0, and everything's shut off, and S2 has been unaffected. Whereas that is impossible to happen. Well, S2 would have to increase, right? S1 would go to 0, and S2 would. So you can see fundamentally different behavior. This is just an observation. I mean, my guess is if you simulate both for the models you've shown, you're going to see similar behavior.
yeah, that
But
would be my guess.
It's almost like 5 is a two-step version of 6, right? It's like if you break up the S1 being destroyed and the S2 being
I mean, what
created.
you've done is you've taken one
Yes.
counting process
Right.
and you split it into 2 counting processes.
Yeah, I would expect like qualitatively similar behavior.
There's a good
Yeah,
theorem
but
sitting
the-
there to be proven. When do you get to say, how do you quantify
The
that?
thing that still bothers me about this is, I mean, it depends a little bit on, how many reactions you have and how fast they are, because if you think about, I mean, you're writing things down as mean fields, right?
Mhm.
And so in those 2 phase planes, you said, in the original problem, you just go to the fixed point, it's boring, right?
Mhm.
But then you change it, so suddenly more stuff is happening. But if you just look at those as 2 ODE systems that are somehow transformations of each other, then they do different things under the noise.
What do you mean? Oh, you mean 2 OD systems corresponding to 2 different reaction networks?
Yeah.
Um,
So, I mean, never mind the fact, I'm not talking about reactions, I'm just saying, you have 2 ODE systems. At some stage, you don't care whether one goes negative or the other one, right? One is just transformation of the
Yeah.
other. But in one case, you go to the fixed point if you have, some noise. In the other case, you can switch back and forth between the other 2.
I guess, but I mean, if you mean by original systems the one that has cross-negative terms, that we cannot really represent chemically at all.
No, I'm not saying represent it chemically, I'm saying it's a mean field of some system with, that you could write as the limit of some stochastic network with fluctuation.
In a way, yes, but
But it wouldn't be chemical, would it? I mean,
Well, Kurt's-
because it's kind of negative. I thought that.
No, I'm not saying, all I'm saying is though, this is back to what David is saying, is that you could have totally different stochastic behaviors, if
that.
you
That's
started
okay,
with
right.
two stochastic systems and transformed one into the other, at least according to your mean field thing. So that's all I'm saying, is you may have changed the underlying stochastic.
Yeah, but for example, if we, okay, yeah, but also it's a question of what stochastic process we choose for our model, because for example, if we choose Langevin equation, for example, it will be equivalent in all the chemical reaction networks.
Sorry, you're saying that the Langevin statement is going to be invariant against which choice you make?
Of reaction network, because it completely is induced by the coefficients in the deterministic function.
No, it can't be.
Really? Like,
I mean, what I was just saying to Pete is, like, reaction network 5, the state space is all of Z2, the non-negative portion of Z2. Whereas the state space for 6 is a one-dimensional, right? It's a line in Z2, right? And so even the Langevin approximations will satisfy those same things also. So even the state spaces are different. Is that what you were?
no, I mean, I would assume that the structure of the Langevin equation will be kind of deducible from the ODEs solely, so by the terms in ODEs.
I think you have extra noisiness in.
Yeah, you can have other
It's a question whether you
correlations and
use
things
the
going
same
on.
noise in the two equations, R1 and R2, or two different independent.
Sure. So, but from the standard Langevin construction, if you started with 5, you get 2 independent sources of noise.
Right, exactly.
And so you're going to be bopped off the line.
And in fact, like
That's
the
a
noise will be
technical
twice
term,
as strong.
bopped off the line.
But also, I mean, in
So
the
that
case of the Langevin equation, you can, isn't it the case that even for a given reaction network, you can formulate the noise in different ways,
Yes.
but they all turn out to give the same dynamics, as far as I understand. No? No?
I think
If
If you specify the reactions, right, they're sort of the right way to do the noise. But if you just know the mean field log, that's not so clear to me.
Yeah, if the reactions don't change, but in this case, you have two different sets of reactions, right? So then you're gonna have different correlations.
I think what is true is in equation 5, for example, you could in principle, I'm not saying that you actually can, but you could in principle write it with 2 Brownian motions or 1 Brownian motion. And then these two descriptions for equation 5 would be equivalent from the point of view of probability. But that doesn't necessarily say that it would be equivalent between 5 and 6, if you see what I'm saying.
Well, but if
Yeah,
you use
yeah.
the same Brownian motion for the 2 reaction channels in 5, then you would get the same as for 6.
And you would need to do it.
That's the point.
Yeah, but
Exactly,
that's not how we typically
Yeah.
derive these things.
exactly.
If you write down a Fokker-Planck equation, and then if you start from the Fokker-Planck equation, then you are free to choose whatever
Yeah, yeah.
Brownian
Well,
motion
that's
you want
exactly.
to come back to the Fokker-Planck equation. But starting from this, I'm not sure.
If 6
You have
is
to
just
specify.
correlating perfectly the noises in 5. Right?
Exactly,
That's right.
exactly.
But the question then is, okay, if you were to write down just the Fokker-Planck equation for 5, and just the Fokker-Planck equation for 6, they won't be the same.
Oh, no.
No.
I mean, think of the state spaces. So the state space for 5 is a triangle, like you have a line. Okay.
There is chalk there.
Okay, you don't mind. I mean, the state space.
Sorry?
If I'm
Stop recording? Okay.